So let's look at some advanced methods to solving trigonometric equations. Let's just dive right into the questions. First question here. Negative 3 sine x minus 1 equals 1. How do we solve this equation? Well, similar to solving any other equation for x, we have to isolate x. Unfortunately, we can't isolate x because it's inside of the sine, right? So let's isolate the sine x term first. And that's the first strategy you see up here in italics. Isolate the sine x, right? So we're going to get sine x equals, if I move that 1 over, we get 2. And then we're going to divide both sides by negative 3 to get sine x equals 2 over negative 3, or negative 2/3. Okay, that's cool. Now, how do we solve for x? Well, this isn't one of our trig ratios that we can find the exact values for. So essentially, all we have to do is to undo that, sine x, we have to take the inverse sine x, right? So essentially, x is going to equal sine inverse of 2 over negative 3. There we go. What do we do with this now? We can plug it into our calculator. And if I do that, I get x comes out to approximately 0.7297, negative 0.7297. So is that it? Is that our answer? Well, technically that is a answer, but is it the only answer? Think back to when we were solving sinusoidals. It's not the only answer. We're asked to find all answers between 0 and 2 pi, right? So, by the way, this is a radian measure. My calculator is in radian mode, so that negative 0.7297 is a radian measure. So before going further, let's actually find out what this equation means. So I'm going to throw a few things into Desmos, and let's see what it gives us. So here, I've graphed the two sides of that equation, the left side and the right side in Desmos. And you see this is what we're given. I make sure that Desmos is in radian mode because that's what we're working with in this course. So if you look here, this right side, the left side of the equation is that red line, and the right side is the blue line. So when we're solving this equation, remember what that means is basically we're finding where these two things intersect, the x values where these two things intersect. So by doing this work over here, what did we find? We found an x, a solution, at negative 0.7297. So we found, if we look here on the graph, we found this point right here, right? Is that an answer we're actually looking for? Let's go back to our question. Our question's asking us to solve each equation where x is between 0 and 2 pi. So is this actually a solution to our problem? No, it's not. And that's why we always have to be careful. We can't just do the algebra. We need to do a little bit more work when it comes to sinusoidals. You'll see 2 pi, so between 0 and 2 pi is about 6, right? Just to make things super simple, 2 pi is about 6. So when we're saying we're looking for between 0 and 2 pi, we're basically looking for solutions in this range right here, right? Between this point and this point. So if we look for where those two lines intersect between those 2 points, we should really be looking for a solution here and here, right? So around 4 and around 5.5-ish. And how do we do that? Let's actually go back to our question and let's change some things up. So when we get to this point where the sine is isolated by itself, sine x equals 2 over negative 3, remember, we can draw a sketch of this. Where is sine going to be negative? And the answer is down here and down here, right? In the third and fourth quadrants, that's where sine is going to be negative. So we know we're going to have two solutions in the third and fourth quadrants. Now, when we do this thing in our calculator, what is it actually giving us? It's giving us, essentially it's giving us the smallest angle. And it's giving us negative 0.73 approximately. And that is actually this angle here, right? That's what it's giving us when we do that. We usually call this angle the related acute angle, or beta. And I'm going to show that beta here because that beta is going to be the same thing on this side, right? So when we're doing this, a lot of times the strategy, when we plug this stuff in, is let's actually ignore that negative sign in the sine, right? Instead of solving for this thing, let's actually solve for beta. and we call that sine inverse of, we just ignore the negative, 2/3, right? And what that's going to give us is that 0.7297, right? So let's sort of not do this and just find what that beta is. Because once we have beta, we can easily find the two values that are true. So because we're looking for x between 0 and 2 pi, we're actually looking for the positive angles. So we're looking for the angles that look something like this. The angle that starts here and goes around here, and then the angle that starts here and goes all the way around to here. And we can call those solutions, because our variable is x, we can call those solutions x1 for the small one and x2 for the big one. So how do we find x1? Well, if we look, it's just like you've gone around 180 degrees or pi degrees plus beta. So we can find x1 is just going to be 0.7297 plus pi, which gives us a value of approximately 0.7297 plus 3.14159, 3.87. And of course, that is in radians, right? It's an angle in radians. x2, to find x2, it's like you're going all the way around the circle, right? And then you're subtracting that beta. So it's like you're saying 2 pi minus 0.7297, which gives us a value of minus 0.7297, which gives us a value of 5.55 radians. Are those the only two solutions? Well, if you think about it, those angles, first of all, think about it, are those angles both between 0 and 2 pi? And the answer is yeah. 2 pi, remember, is about 6-ish, and 0, obviously, they're greater than 0 and less than that. So these are two solutions that seem to work. Let's look at, and our graph also shows that, our circle here that we drew also shows that. It's less than 2 pi. It's within one rotation of the circle. But the other way to see that is our Desmos graph, right? Didn't we predict that the solutions be around 4 and around 5.5? And that's exactly what Desmos shows us. So those are the two solutions to this problem. So now let's look at this second problem here. First step is to isolate x, right? Or at least the thing with x in it. So let's try to isolate tan x. So what I can do, I can start off by moving that 5 tan x to the other side. So it's going to be 3 tan x minus 5 tan x, which is going to give us negative 2 tan x equals negative 2 root 3. Divide both sides by negative 2 to get rid of that. So we're going to end up with tan x equals root 3. So feel free to pause the video here, see if you can find the solution or solutions to this answer here. Okay, so again, our first step should be, let's draw a quick sketch. Where is tan positive? Tan is positive in the second quadrant and the fourth quadrant, right? And what we're going to solve for here is our beta, our related acute angle, and that's going to be the angle to the x-axis here and the angle to the x-axis here. So let's find beta first. So to find beta, it's just going to be, beta is going to be the tan inverse of root 3. So we can easily do that, inverse tan of root 3, which gives us 1.01472. So beta equals 1.0472. Right? So that is what our beta is. Now, can we find our x1, we'll call this x1, and our x2? So x1, realize x1 is just going to be equal to that beta. It's the same thing. It's just our related acute angle, 1.0, and I'll round this to 2 decimal places for our final answer, so 1.05 radians. And then x2 is just going to be pi plus that beta. So pi plus 1.05 is going to give us, plus 1.05 is 4.19. There we go. Two solutions. Are there any more solutions between 0 and 2 pi? It doesn't look like it, because those are the only two quadrants that, that tan can be positive. So the next question actually looks sort of similar to our previous question, right? The previous question had us solve for tan x, which equals root 3. The only difference here is that we have tan 4x equals root 3. Now, how does this make the question any different? Well, drawing our quick sketch again for tan x, right? Where is it going to be positive? Because I know there's a 4 in there, but we're still looking for where tan x is a positive number, right? Because 4 multiplying by 4 isn't going to change whether it's positive or negative, right? So essentially it's asking for where is tan x positive? And we know it's going to be there, right? Those two quadrants, quadrant 1 and quadrant 3. So if we solve for our related acute angle again, we know we can do that to find beta. But before we do that, I'm going to simplify the question a little bit, because that 4x inside the tan makes things more confusing. I don't like it. So what we're going to do is we're actually going to make a substitution. I'm going to say let 4x equal u. I'm just going to use u as a variable for a substitution. So if we do that, we can rewrite our equation out now as tan u equals root 3. So let's just forget about that x altogether, solve for u, and then deal with that x later. Okay? So if we do the beta of this, the related acute angle, we can solve for that as beta is going to be the tan inverse of root 3. And we know beta, same as the previous question, it's 1.0472. That's going to be our beta, right? So because I made that substitution, essentially what we're going to solve for with that beta is a value here, u1. So we're going to get one solution for u, and then we're going to get two solutions for u, u2, right? And we can do the same process as the previous question. u1 is just going to equal beta, so it's 1.0472 radians. And u2 is just going to be pi plus 1.0472, which comes out to 4.19 radians, right? And actually, let's round this one as well to 2 decimal places, 1.05 radians. So these are two answers for u. Are we done? Have we found our solutions? Well, remember, the goal of this question was not to solve for u. It was to solve for x, right? So we found two things, but we didn't actually solve for x. We solved for u. So what we can do is we can unsubstitute those values, right? We know u1 is going to equal 4 times our x1. That'll give us one x1 value, right? So in order to solve for x1 is just going to equal our u1 value divided by 4, right? So u1 was 1.05, and then we can divide by 4 to give us an x1 value of 1.05 divided by 4 is 0.26. So our x1 value is actually 0.26, and we can do the same thing for x2, right? It's going to be u2 over 4, which is going to give us 4.19 divided by 4, gives us 1.05 radians. Radians, right? So we have two solutions here. Are we done? We found two x values that correspond to that just by finding the u values. Are we done? Well, just like the previous question, let's throw it into Desmos and see if these are the two answers to the problem. So here we go. I threw that into Desmos. Okay, so we found two solutions. The red line intersects with the blue line. We found a 0.26, which looks like it's going to be this solution here. This solution here. And then we found 1.05, which looks like it's going to be this solution there. Cool, so we found two solutions to this problem. Are we done? Well, think about what the question was actually asking us for. Zooming back out, going back up here. The question asked us to solve each equation between 0 and 2 pi. So that means we want to solve the question between 0 and 2 pi, which is about 6, right? So we're looking for all the solutions between 0 and 2 pi. Are those the only two solutions? No, they're not. right? We actually have a solution here, we have a solution here, we have a solution here, 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 here. We got lots more solutions. In fact, we got 6 more solutions to this problem. So the question is, how do we actually find these values? Think about it if you want, pause it if you want, and then we will discuss. So the idea is, in order to find these other values, wouldn't it be handy if we can find out how long a cycle is, or how long a period is? Because think about it this way. Isn't each of these solutions, if we zoom in here, isn't this solution, these two solutions, how far apart are they? Aren't they just one cycle apart? Right? They're one full cycle of tan x apart, right? And these two are another full cycle of tan x apart. And these two are another full cycle of tan x apart, right? So each one of these is one cycle apart. So if we knew the period of this function, if we just added one period each time, so this is one period here, this is one period here, if we kept on adding one period, we should be able to find those answers. So this is actually where our knowledge of function transformations comes into play. How much is one period of a regular tan function, an untransformed tan function? Well, if you remember from previous lessons, the period of sine and cosine are 2 pi. It's one full cycle of the circle. But tan actually repeats after pi, right? The cycle is only essentially 180 degrees. So regularly, tan has a period of pi. But what's different about this function? What's going to be the period of this function? Well, the k value in front of that x is actually 4. So what that tells us, remember, our relation between k and the period is that the period is going to equal our pi divided by k. And that's because a regular tan function has a period of pi, and then we divide by that k value, which is 4. So essentially, our period of our function here is going to be pi by 4. Okay, so that tells us that the period of this function is pi by 4. So that's what these sort of the difference in these values were, right? They're pi by 4 apart from each other. To make this easier, we're working with decimals. We might as well convert that to decimals. So that actually comes out to, if we divide pi by 4, we get about 0.79 is one period, the length of one period. So let's start from the first x value, the first solution here, and let's add periods until we get to our limit of about 2 pi, right, about 6. So let's see what happens. Our first solution was 0.26 radians. If we add a period to that, we get 0.26 plus 0.79, which gives us x2. It gives us our second solution. So we already have that as a solution. We don't need to add it again. But to find our x3, our third solution, we could do 1.05 and then add a period, 0.79. What does that give us? Let's see, 0.79 gives us 1.84 radians. Then we can keep going. x4 is going to be 1.84 plus 0.79, another period. We're going to get 0.79 plus 0.79, which is, oops, I added 79. It should come up to 2.63 radians. Continuing on, we have a fifth solution. If we add 0.79 again, 3.4, oops. So we would do actually 2.63 plus 0.79 gives us 3.42 radians. And we can keep on going. X6 is 3.42 plus 0.79 equals, plus 0.79 is 4.21 radians. Now the thing we have to be keeping in mind is we want to find all the solutions between 0 and 2 pi. Are we at 2 pi yet? No, because 2 pi is just over 6, right? So we're not there yet, so we have to keep going. X7 is going to be 5 on the dot, well, according to our rounding. So if we do 4.21 plus 0.79 That's going to bring us to 5 radians. And then one more time, if we add that, x8, it's going to give us 5 plus 0.79 is going to give us 5.79 radians. We can add it again, and we find out it comes out to 6.58. But 6.58 is greater than 2 pi. 2 pi is actually 6.28, so we don't need to keep going. These are our solutions. So going back to the actual graph, just to clarify, I know it's been a bit of a crazy question, but to clarify what's going on here, we needed to find all these 8 solutions to this problem between 0 and 2 pi. And we did that by just adding periods each time. Okay, remember we had to find our period because it's like a regular tan curve, which is pi, and then we had to divide it by the k value because it's like that tan curve got compressed by a factor of 4. Okay, so this is a bit crazy that we have 8 solutions here. Hopefully the next question doesn't have quite as many solutions. So moving on to D, notice how I changed the question from cotangent to sine just to make it a little bit different than the previous question. Hopefully in your handout I've already corrected that. But anyways, let's start by just isolating the thing with x in it, the sine 2x. So I'm going to bring the 6 over to the left side. I'm going to get negative 4 sine 2x is equal to, bring the 8 to the other side, equals 2. So that means sine 2x is going to equal negative 1/2. Okay, that's fine. That's all well and good. Again, I don't like that 2x inside the sign. It makes things a little bit confusing. So let's make a substitution. Let's let 2x equal u. Let's call that u. So our new equation would be sine of u equals negative 1/2. So drawing a quick sketch, where is sine going to be negative? Down here and down here, correct? And we can actually solve for the related acute angle, the beta, right? Just by taking the inverse sine. So we're going to say beta. Beta equals the inverse sine of 1/2, right? Let's forget about that negative sign for a second. So beta comes out to, in this case, that's actually one of our values. So one of our values on our unit circle, or our special triangles. Where does sine equal 1/2? And again, look back at your unit circle if you need a refresher, but sine equals 1/2 at pi by 6. Exactly pi by 6. That's an exact answer. So if beta equals pi by 6, can we find our solutions? Can we find our u1, our first solution, and u2? Can we find those? Yeah, we can. u1 is just going to equal pi plus pi by 6, right? Because it's just that, that going around, which is the angle 7 pi by 6. And then u2 is like saying 360 or 2 pi, right, all the way around, minus that beta, right? So it's like saying 2 pi minus pi by 6, which is going to give us 11 pi by 6. Okay, so we found our 2 u values that correspond to that first 360, that first rotation of the circle. But remember, we're not here to solve for u. We're here to solve for x. So let's back up a little bit. Let's actually solve for x now. So x1, I'm actually just going to write it sort of underneath here. x1 is going to equal, well, if we rearrange our equation here, right, it's going to just be u divided by 2, right? So it's going to be our u1 divided by 2, which gives us a value of 7 pi by 6 divided by 2 is going to be 7 pi by 12, right? And our x2 value is just going to be u2 divided by 2, which is going to be 11 pi by 6 divided by 2, which is 11 pi by 12. So that's good. We found our first 2 solutions of x, right? And it occurs at 7 pi by 12 and 11 pi by 12. Are those the only 2 solutions, though? Well, let's think about it this way. Instead of drawing it in Desmos, I'm actually just going to draw a quick sketch of Sine X. We know Sine X looks something like this, right? And for our regular untransformed Sine X, we know it repeats at 2 pi radians, right? So this is essentially asking where this intersects with the value of -1/2, right? That's what sort of the question was asking, where this intersects with a value of -1/2. So down here. And just by this, we can see that it's going to intersect here and here, right? But we're not actually given sine x to transform. We're given sine 2x. So what did the k value do to this relation? It actually squished it, right, by a factor of 2. So between 0 and 2 pi, instead of 1 cycle, we actually have, let's see if I can get this right. We actually have 2 cycles, right? Because it's been squished by a factor of 2. So now if you look at where our solutions are, we actually have 1 solution, 2 solution, 3 solution, 4 solutions, right? We actually have 4 solutions that we can solve for because it's been squished. So how do we find those solutions? Well, we have our first 2, so we're good because we have this one here and this one here, right, in our first cycle, and that's what these 2 solutions refer to. How do we find these other 2? We can find them because this solution over here is just 1 cycle later of this solution, right? And this solution here is just 1 cycle later of this solution. So if we know what 1 cycle is for this function, we can just add a cycle to this, add a cycle to this to find our final solution, right? So that's exactly what we're going to do. How do we find the length of a cycle? Well, another name for that is the period, right? So the period, this time it's going to be 2 pi because a regular sine graph has a period of 2 pi, and we're going to divide that by our k value of 2, right? So essentially our new period is just pi, which makes sense because it's half of the original period of 2 pi. So in order to find x3 and x4, our third and fourth solution, all we need to do is add pi to each of those solutions. So x3, I'm just going to do 7 pi by 12 plus pi. And that's actually going to give me, let's add 12 to 7, that's 19 pi by 12. And our x4 is just going to be 11 pi by 12 plus our pi, which gives us 11 plus 12 is 23 pi by 12. Are we still less than 2 pi? Just double check. And the answer is yes. 2 pi would be 24 divided by 12, right? 24 pi over 12. So we're still less than that. So we found our 1, 2, 3, 4 solutions for between 0 and 2 pi. So just taking a step back and looking at these 2 questions, they can be a little bit tricky. They look a little bit daunting. But remember, the basic steps are basically the same. The first step is to solve for the variable, right? So in this case, or solve for the thing with the variable in it. So solve for sine 2x, or in this case, it was solve for tan 4x, which is already isolated. Then I like to make a substitution in order to make that equation simpler. Then find your beta values, find the solutions to that new equation with the u's in it, right? Which in this case was over here, in this case was over here. And then go back to find out what your x values that correspond to that would be. Once you have those x values, make sure there are no other solutions that you can find between 0 and 2 pi, or whatever range you're given. In both of these cases that we had here, the k value compressed the function. So that means there's going to basically, it's going to be introducing more solutions between 0 and 2 pi. So whenever you need to do that, find the period and just add the period onto the solutions you already have to find where there's those new solutions are. Okay?